All right.
All right.
Let me, yeah.
Oh, yeah.
You first. So today we have Ira Globus Harris speaking our seminar. Ira is a second-year PhD student of computer science at the University of Pennsylvania, where they work with Aaron Roth and Michael Kearns. Ira's research interests include algorithmic fairness and differentially private learning on small data sets. Before coming to Penn, Ira was a software engineer at Boston University, where they developed differentially private software libraries in collaboration with the OpenDP project. And aligned with their research in fairness, Ira cares deeply about improving equity and inclusion in computer science. For example, they run the group for LGBTQ+ graduate and professional students at the University of Pennsylvania's School for Engineering and Applied Sciences. And today we are very excited to hear about Ira's work on lexicographic fairness. Ira, you can take it away.
All right. First of all, can everyone hear me and see my screen?
Yes.
Great.
Yes.
Cool. All right. Thank you, Said, for the introduction. Like he said, my name's Ira. My pronouns are they, them. And today I'm going to be talking to you about this work on lexicographically fair learning. This is joint work with Emily, Diana, Wes Gill, Michael Kearns, Aaron Roth, and our own Said, and was published in Fork 2021. All right, so, oh, come on. All right, so in general, as we all know, we would like our algorithms to treat different groups of people equitably. And I specifically use the word equity here rather than equality, because I don't really think of those two things as the same. So in general, right, when we talk about equity in society, that doesn't necessarily mean that a particular process is going to behave equally for every single group of people. For example, in like a resource allocation setting, you know, if one group of people, say you're, I don't know, allocating rice to different groups of people, and one group of people already has a bunch of rice. You don't want to allocate the same amount of rice to every single group. You want to allocate the rice to the groups that don't have any rice. So it's not that every single part of the process is going to be equal. It's that the overall result is something that maybe like in an overall sense promotes equality, but that's like more broad. The actual algorithm might not be doing that. So that's just like a general framework that I approach things with. And so thinking about how this relates to fairness, well, traditionally we have notions of group fairness that rely pretty heavily on equality as the thing that we're trying to take this philosophical notion of fairness and apply to our algorithmic setting, right? So the idea here is that the algorithm should make the same number of mistakes on all groups. So here model H1 would be unfair and model 2 would be fair. And in many settings, this might be something that really does make sense, but it might not in every setting, right? Specifically, one thing that we might see happen is that, you know, if the underlying Bayes error associated with each group is different, which it very well could be, then in order to get equality of group errors, we might have to artificially inflate the errors of other groups. And it's not like increasing the error on one group is creating a gain in another group. It's that just to get this basic equality, we're doing this inflation. And this might be bad for a couple different reasons. First of all, maybe that's just really not what we mean by fairness, right? Like maybe what we mean by fairness is something along the lines of we want to be doing the best possible for each group. Or, you know, yeah, I think especially if you imagine that groups G2 and groups G3 in this case are also disadvantaged groups, you know, it would really rub us the wrong way to think, oh, we're taking these disadvantaged groups and we're making performance worse on them. Furthermore, just from a practical standpoint, it can be really, you know, I at least would like to see fairness be applied in the real world to industry applications. I don't necessarily know that it's a fix-all for all ethical problems and relating to bias and fairness for algorithms, but I think it's a step in the right direction. And it's a hard sell to an industry service provider to say, hey, we'd like to take your model and we'd like to make it worse. We'd like to, make that overall error a lot worse. They're going to be hard pressed to agree to that. So, well, what can we do? We can think about alternative ways of reframing this problem, right? So, for example, we could just think about minimizing error for the groups, right? And something sort of in this general line of thought is the idea of minimax group fairness, which says, okay, well, the number of errors made on the worst off group should be minimized, right? Let's think about, instead of equalizing group error, let's just look at the group that we're doing the worst on, and let's try to get the best possible thing on that group, right? So this is a step in the right direction, but it's not really necessarily all the way there, because there's some remaining problems. If you only have 2 groups total, maybe this seems pretty good, but what happens when you have more than 2 groups? And then you have to do things like break ties between different mini-max solutions, right? Like, how do I decide that I'd like to choose model 1 versus model 2 here, where model 1 performs better on group 3 and model 2 performs better on group 2, but they both minimize the maximum group error over group 1. Like, how do I make that choice? That's not something that could be a policy decision, but it doesn't seem like we're quite doing everything here. And one observation to make is that part of the reason this is happening is that we're kind of leaving money on the table, right? We're minimizing the maximum group error, but we're not really thinking about any of the other groups. So sort of a natural extension of this idea is what we're calling lexicographic fairness, which says, well, we want to minimize the worst off group's error, but subject to that, we'd also like to minimize the second worst off group's error, and so on and so forth. So we take our initial we take group 1, which has the worst error. We want to minimize that, and then we say, okay, can we do better than that on the other groups? Subject to that first minimization, can I get group 2's error lower? If so, yes. Okay. Now moving on to group 3, can I minimize that group error? And then the resulting thing would be what we'd call the lexicographically fair model. So the group errors aren't equal, but we're trying to do like the best possible for every single group, subject to the previously worst off groups minimization procedure. So this is great, right? It seems like a fairly natural extension to minimax fairness. It doesn't seem too awful, but there's a catch, right? So we can only get approximate minimax fairness. So, in order to minimize that first worst group's error, we can only guarantee that we have like within alpha of that error. So this is fine when we're just doing one of these steps, but how do we generalize this notion of approximate fairness when we're thinking about fairness over these iterations through the groups? So the first natural, or at least what I thought was the natural thing to do, was to just say, okay, well, if the original LexiFair solution is H under no approximation, if this is the best thing we can do over all of these groups, then why can't we just say, okay, I'm going to require that the lexicographically fair solution is within alpha, or has each of these group errors is within alpha of what they would have been without the approximation. And this seems reasonable. It seems like something we'd want, but it turns out to be tricky to get to that, because what happens is that there's sort of an instability in the definition. So if we take this example where we have 3 groups and the true LexiFair solution has the first two groups with error 0.5, and then the third group has error 0. And then we say, okay, we want to get an approximate Lexi-fair solution where the first two groups have, error within alpha of 0.5, and the third group has error less than or equal to alpha. Okay, so let's see what happens. So in the first group, we maybe we get something that's like 0.55, right? And that's fine as long as it's, our alpha is, 0.05. Now we're going to try to find the error of the second group constrained to the error of the first group being 0.55. But what could happen here is that because of this additional slack allotted to the error of group 1, maybe we're able to get like a big win for group 2. Now group 2's error has gone from being 0.5 all the way down to 0.25. And that's fine, right? We're happy if we can get something that's, better than what it was before. So we keep going. But now, because the second group's error is much lower than it was previously, we might end up with a case where the third group's error actually ends up being really inflated. And it ends up specifically being inflated to much higher than alpha. So it's not really clear how to get this approximate Lexi-fair solution, given how we're iterating through our groups recursively. So what we do instead is we develop this more stable definition where the error of the ith group is defined recursively in terms of the previously minimized errors. So if we think back to this picture, this third, if we set that this group's error has to be within alpha of what the Lexi-fair solution would be subject to whatever this group's error was chosen to be, then we're fine. So that's all that this definition formalizes. And specifically, so it requires that the solution satisfies an alpha bound for some sequence epsilon 1 through epsilon L, where L is the number of groups, which are component-wise less than alpha. And so this notion where you were recursively defining what we mean by fairness, subject to what the previous models, previous error rates were for the previous groups that have already been established, successfully avoids this instability. Okay. So, where do we go from here? The first thing we want to think about is, okay, is this definition convex, right? So if we're just thinking about the minimax fairness definition, right? If we're just minimizing the maximum error, that is a convex problem. So we can optimize over it. But in general, now we're thinking about things like the second highest group error, third highest group error, etc. And if we're just thinking about those things in isolation, optimizing that's not necessarily a convex problem. So to think about this, imagine we have two solutions. We've got one that has group error of group 1 of 0.5 and group error group 2 of 0, and the other one that's the same thing but reversed. So these two solutions, both of them have second highest error of 0, right? But a convex combination of them, you can think of the mixture that's half and half of them, has second highest error that's greater than 0. So it's non-convex. So, and right, we care about this because we'd like to be able to say that if you have like a convex combination of fair models, that the result is fair, and that makes it a lot easier to actually find anything. So the question is, well, okay, are we hosed? And luckily for us, we're not, because something that I sort of shoved under the rug when I was talking about the convexity argument is that we're not really just thinking about the the kth largest error in isolation. We're thinking about it subject to the previous k-1 largest errors already being constrained. So you could think, well, maybe this helps. Another thing we could think of is we'll say, okay, well, maybe I can just, rewrite our notion of Lexi-fairness in a way that kind of forces convexity. So one way to do this would be we could constrain the sum of group errors of all subsets of groups of size j instead of just thinking about the jth highest group error. Now, because these are sums, they're all nicely convex. And even though we're increasing the number of constraints, we have, everything's hunky-dory. And it actually turns out that this alternate notion is equivalent to the original notion of approximate Lexi-fairness, as long as you're not thinking about approximation. So as long as approximation, the alpha parameter is equal to 0, this is actually a completely equivalent definition. We're not quite sure how they relate when the approximation is non-zero, but there's potentially some sort of relationship there. And the reason, the intuition for this is just because since we've already constrained a bunch of previous errors, the convex definition is really just still boiling down to constraints on just the jth largest error. So you end up with the same thing. Okay, so far we've got a nice definition that satisfies stability and satisfies convexity. So what's missing? Well, I haven't really said anything about how to find a model that's Lexi-fair, right? I've just presented a definition. So we're going to do this by first, we're going to take the feasibility problem and we're going to rewrite it as a minimax problem. And then because of that, the minimax theorem will apply and we can solve them using no regret dynamics. And it's going to look like two different things in the regression and the classification setting. So in more detail, let's just think about really like still shoving a lot of details under the rug, what you're actually doing when you're trying to find the Lexi-fair solution. So you want to go from worst group through all of the groups. And then given all the previous error rates that you've established, you want to estimate your current error rate up to some alpha using some sort of algorithm that returns a model that satisfies that level of Lexi-fairness, right? So again, because Lexi-fairness is recursive, if you have Lexi-fairness on like the j-1 things, and then we have a way of just of getting a Lexi-fair thing for the that j thing, then we can sort of inductively apply this for all L groups and then output the resulting hypothesis. So if we're just looking at the jth iteration of this, right, we're given the error rates from previous rounds and we want to get the jth rate, which is this minimization over all of these different losses incurred by the model. So we've got some sort of like, this is just like a gross constrained optimization problem with a bunch of parameters, right? And so the key to notice is that we can then convert this to an unconstrained mini-max problem by using Lagrangian duality. You don't really have to worry about what these terms look like. Just think, okay, we're converting to the dual. Oops. And that's great. We have this lovely gross dual, but we still have to actually solve that Lagrangian, right? Just the minimax solution for it. So basically what that Lagrangian is we've rewritten the problem of, or the minimax problem really, is we've rewritten the problem of finding the eta sub j's, the problem where we're taking the minimum over all of our models constrained by all the previous error rates, and then we're taking the maximum over some combination of like j possible groups. And fun fact, we can use no regret dynamics to solve a 2-player game between the minimizing and the maximizing players to do this. You can pretend that like the minimizing thing and the maximizing thing are 2 different players and they're talking back and forth to try to get the optimum solution. So how this is going to work is the minimum player is going to be updating its strategy according to a no regret learning algorithm. And then the maximum player will be deploying its best response to whatever that action was, and they're going to go back and forth, and it turns out that the average plays form an approximate solution. And this is, it's like a well-known fact to some people. It was not well known to me before writing this paper. Okay, so that's cool. So now we've got this like general 2-player game formulation, but we still need to figure out what that no regret learning algorithm is, right? So it's going to depend on our setting, right? In the regression setting, our models are some parameters theta in some like nice convex domain, and we have these lovely errors that are convex loss functions. So that's all hunky-dory, and we can use gradient descent as our no regret algorithm. So specifically what this is going to look like is we're going to go through our, L groups, given our alpha approximate errors from the previous j-1 steps. We're going to play some number of rounds of a game where the minimum player uses gradient descent to get their parameters for that round. They'll compute the error given that round, and then the max player will best respond. And then they'll keep running that, and then eventually they'll output some eta to sub j and theta in terms of that. And then they'll output those final parameters at the end of the L rounds. In the classification setting, things are a little bit trickier. Right now we've got binary classifiers, and our errors are given by 0-1 loss. So we have to linearize that error. So we think about expected 0-1 loss across all possible distributions. And then we're able to use follow the perturbed leader, which has to have access to an ERM oracle as our no regret algorithm. So follow the perturbed leader is another method where instead of gradient descent, where at every round t, our learner is going to be choosing some action, and then the adversary plays a loss vector, and the learner incurs a loss that's the direct product of that loss and their action. And the way that the learner chooses an action is it looks at all of its actions from the previous steps. It tries to optimize over those, and it also perturbs that, that should be xi, sorry, by a uniform random variable that's also scaled by the some learning rate that's been established. So, right, so what this looks like is that, through the L steps of the algorithm, and given the previous error rates, the minimizing player uses follow the perturbed leader, and it does this sort of internal process to get H of that round. It computes its loss for the round, and then the maximizing player best responds. And again, it computes the noise rates, and it outputs the parameters for the classification problem. So now we've got, a general 2-player game formulation that we could essentially apply to any learning problem that we wanted to. And we've got some Oracle efficient algorithms for regression and classification, which might be the 2 things that you want to do most. But what we haven't talked about is what we can say about generalization guarantees of the algorithm, right? Because it would be nice to say, not only am I fair over the sample, but I'm also fair over the distribution, right? My model is fair, I mean. So we're able to show under particular settings. So if our base hypothesis class satisfies like a uniform convergence bound, and if we're given some model H that is lexi-fair on some data set sampled from that distribution for some distribution, then that hypothesis is lexicographically fair under the underlying distribution. So of course, I'm hiding a bunch of things with this simplified version. The formal guarantee is that if our hypothesis class is some binary set of binary classifiers, and we've got VC dimension D, then we can say with high probability, or with probability 1 minus delta, that we get an L alpha plus epsilon lexi-fair thing over the distribution, as long as the smallest group size is O of this gross thing. I have talked way faster than I thought I was going to. Sorry, folks. So hopefully it's okay if we just switch to like a discussion for the last chunk. Does anyone have questions?
Yeah, that's totally fine. Like if anybody has questions, they can unmute themselves and.
I have a question. In the description, it looked like the groups, like in the drawing, it looked like the groups were disjoint. But like, is it like the groups can be, they have to be disjoint, or does it work in general?
I don't think that we do anything that requires the groups to be disjoint. That's a good question. Let me think. No, I don't think so. Saeed, do you agree with that?
Yes, I think we do allow for groups having an intersection with each other. Yeah. Any other questions?
So two aspects that perhaps went too quickly for me. One is the convexity. I'd be happy if you explain it again. But the other one is robustness. You showed that the other definition is not robust, but is there a notion of robustness that you're proving, or?
Are you referring to the stability discussion?
Stability, yes, thank you. Yeah.
Okay. Yeah, so, okay, let me go back to the earlier slides. Yeah, I went too fast. I'm sorry. I previously gave a 5-minute version of this talk, and so apparently it's talking way too fast. I'm just skimming over things. Okay. Okay. So, right. What do we mean by stability here? What I'm referring to is the fact, so the definition of lexicographic fairness is sort of, it's inherently recursive, right? So we're talking about like the second worst error, and that worst error is, relative to the first worst error being the most worst, the most worst. Is that second worst error is relative to the worst error already being minimized, right? And so given this recursive notion, the argument is that once you allow for slackness and once you allow for approximation, then the result that you get like won't be within like if we tried to require that all of the group errors were within alpha of the true Lexi-fair solution, we end up like we can't get that. And the reason we can't get that is because the group errors, like as soon as you add slackness to the first group error, and now you're considering what happens after that thing is set, as you go down through your group errors, you can have these like spectacular blow-ups of group error.
Yeah, I understand that. You explained it very well. So I understand that stability means with respect to the recursive algorithm.
Yeah.
And errors. Perfect. Thank you.
Yeah. Okay. That was, sorry, that was your sentence that you just said was a better way of saying what I just said.
And maybe then, another, just to
yeah.
say one thing, like another way to think about this, it's not necessarily something that has to do with the algorithm. Like you imagine comparing the exact Lexi-fair solution on the distribution with the exact Lexi-fair solution on the data. Like the best thing you could hope to do is to come up with like the exact Lexi-fair solution on the data. What Ira's picture is showing is that if you used this unstable definition, like the vector of errors you would get on the exact Lexi-fair solution on the data could be like arbitrarily different than the vector of errors corresponding to the exact Lexi-fair solution on the distribution, because even tiny variation in the max error could sort of propagate into arbitrarily large sort of variation in like the third largest error in the exact solution.
Yeah, thank you, Aaron. And then going to your question about the convexity. Okay. So did you follow why it's not convex, and you just want me to go over like how we enforce the convexity?
Exactly. Thank you.
Okay. So okay. So right. I kind of was vague about, did I actually write down? Okay, maybe I should have written down the actual formula that we're talking to here. So what we do is we take our previous definition of Lexi-fairness, which is just thinking about like constraining the jth highest group error. And now we instead think about all subsets of groups of size j, and we constrain the sums of those. And by doing this, because we're taking a sum, we enforce convexity, and we get a set of convex, like all of the constraints individually are convex, so they're all the constraints individually are convex, so then we get a net convex thing from the combination of convex things. Does that make sense?
Yes, thank you.
Okay, I thought about putting in the equation, and then I decided it was too gross. But maybe I should have like made a simple version of it.
No, that's appreciated. We avoiding gross equations is a good goal. Thanks.
Other questions?
Yeah, I had a question about, at the beginning you were talking about how if you were just doing a mini-max on the error of any of the groups, then like you had this issue about tie breaking.
Yeah.
And I don't totally understand how we get rid of that issue here. Like, couldn't there still be times when we have to tie break?
There could still be times where we're tie breaking between like two different, like you could have two sets of Lexi-fair solutions over all of the groups potentially, and you still have to choose which one to pick. But at least we don't have to tie break between two different like we don't have to tie break amid how do I phrase this? So like we'll never have a case where there's subgroup, where there's groups that where we haven't at least tried to minimize the error over those groups, right? And actually, now that I think about it, I'm not actually sure that you can end up with like two. So the concern is that you could have like two different Lexi-fair solutions, right? Like one where group one has the worst possible error that was minimized, and another one maybe you like started off and you minimized group three's error instead.
Yeah, I mean, can't you at any point in the algorithm end up with having to tie break? Maybe I'm just misunderstanding how the algorithm works, but.
I might say this.
You can go ahead, Aaron.
I was just going to say I might motivate this in a way slightly different than tie breaking, because there's, still going to be ties to break. The thing about minimax fairness, which makes a lot of sense if there's two groups, is that it's only talking about the max error group. But then as soon as you generalize beyond two groups, say you try to find the minimum error solution that satisfies this minimax error constraint, right? You're trying to impose this fairness constraint by having this minimax objective, but like as soon as you satisfy the minimax objective, you're breaking ties without any fairness considerations at all, just minimizing average error. And so what this is saying is, well, if there's like 100 groups, say, you don't have to like give up on your fairness objective after you minimize the error of the max group. You can still think about breaking the ties with fairness in mind. So you might want to recursively be minimax optimal on the remaining groups, right? So it's like, rather than avoiding the need to tie break, it's saying, well, the same philosophy that suggested that you minimize the maximum error across groups gives you, you can use that as the tie breaking rule for the 99 remaining groups after you've done that, rather than tie breaking based entirely on, just like average error, giving up on fairness after you minimize the maximum group, which is what would happen if you just tried to solve for the minimax optimal solution.
Yeah.
Thanks. Awesome.
But yeah, you're right that there are still like internal ties. Yes.
Are there more questions for Ira?
Wait, I actually had a question. So I was wondering, in terms of kind of the generalization properties, I'm wondering, so when you when you assume you have a distribution that's not your entire data set, do you assume that you're sampling somewhat proportionally from each group? Because otherwise then your approximation would mean different things if you're sampling kind of disproportionately per group, right? Because one group's approximation error is some value, but if you're sampling 1 point versus like another group, which maybe has a stronger, I don't know, maybe concentration properties based on the number of points you've sampled. I'm wondering.
Yeah. I think that's a really great point, especially, I mean, in the context of fairness, we know that some groups are disproportionately sampled. These generalization bounds were given assuming IID sampling from the distribution, but I think that's a really great point that there should be, and I don't know if, and maybe someone else who knows more could speak to this, but I don't know if a generalization bound is the right spot to think about, you know, what happens when those draws aren't IID, or if you first have like a process that tries to measure like the concentration of different groups representation in the data, and then you do some sort of like pre-processing or something to handle that. I'm not sure like where the sort of concentration considerations should live in the guarantees. But I think that's a really good point that we don't really consider. And I guess a couple of things like along those lines, I think there's some other limitations to this work and the limitations to fairness more generally, or the literature as it currently stands, which is, you know, not only are we assuming that our samples are drawn IID from this data, but we're also assuming that these groups are things that we know about ahead of time, and we assume like they're well-defined things that we know about, and that like the distribution is something that we know about. And I don't necessarily think that those are, and that like the distribution that we're doing that we care about is the distribution that we know about, which aren't necessarily good. They don't necessarily, that doesn't necessarily like parallel reality, right? Because a lot of times you might deploy something and then someone comes along and they're like, hey, you've got a really big problem with this one group of people. And then, you know, we can't deal with that because we're like, well, we already trained the model, unless you want to retrain the model now considering that group. And you know, if the user's data distribution just like doesn't, or their sample doesn't reflect the stuff you trained on, we have no guarantees. So I think that's, your comment sort of reflects some broader issues that I've been thinking a lot about recently.
And I want to quickly mention that the assumption of this generalization guarantees that the smallest group size is at least the bound given. It's not a sample complexity for the entire sample. So I guess that is somehow related to what Judy asked too. Any other questions? All right, if there are no questions, let me stop recording now.